Alright, welcome back to explicit tutorials. In today's video, we are going to look on sets on real number system. After that, we'll solve 2 or 3 examples on our last videos, and that will be all for this video. Before I start this video, I want you to like, share, and subscribe to our YouTube channel. Now, I will start by saying all numbers are complex numbers. Now, I know you must have heard complex number before, and anytime you hear complex number, the first thing that comes to your mind is square root of -1. That is actually correct and not completely, it's not really completely correct. So all numbers are actually complex, both your 2, 3, 4, 5, your 1/2, your square root of 5, both your imaginary numbers, all of them are complex number. A complex number is giving us a plus ib. Now, this a and b are actually any number you know, where I and our I is our square root of -1. This is what we call the imaginary number. So all complex numbers are always in this form. A is any number you know, like your 2, square root of 3, 1, 4, 0.5, and so on. Same thing applies to b. Now, if b is 0, 0 times this I becomes 0. You have a single number. But if b is not 0, you will have an imaginary number. Mind you, square root of -1 in your calculator will tell you mass error. So this is actually in an imaginary world. It does not really exist in real life, in real sense. It does not exist, but it is very useful. Mathematicians use it a lot. So when b is not 0, you will have an imaginary number. So basically, complex numbers are divided into 2. We have the real numbers and we have the imaginary. Real numbers are formed when b is 0, while imaginary numbers are formed when b is not 0. So once b is not 0, every number you want to form here is imaginary. E.g., a plus 5 plus 3i, I is square root of -1. This is imaginary. But anything that makes b 0, such that you have several numbers here, 1, -2, 7, 3, 4, 5, and so on, it becomes a real number. So this real number, mathematicians discover that it is not enough to describe every number as real if this b is 0. It does not really make good sense, because the numbers we have on earth are actually much, and there are some numbers we actually use in our everyday life, while there are some we do not use in our everyday life. So they decided to break it down into 2. So all real numbers are divided into 2. We have the rational numbers and we have the irrational numbers. Irrational numbers. Rational numbers are numbers that can be expressed as a over b, where a and b are whole numbers. A and b here must not be whole numbers, but a and b here must be whole numbers. So any number that can be expressed in this form is called a rational number. E.g., 2/3 is rational because this is a whole number and this is a whole number. 4/5 is rational. This is a whole number and this is a whole number. Your 2 is rational. Why? Because 2 can be written as 2/1. When we say something is whole, we mean it is complete. There's no part missing. That's why we call 3, 2, and all these whole numbers, because they are complete. If it was 2.4, we won't say it's complete because something is missing. It's either it was 3, someone stole 0.6 from that 3, making it 2.4. That is why it's not complete. So the mathematicians that named it whole number have a reason for doing that. When we say something is whole, we are trying to say it is complete. That's why we say this is a whole number, this is a whole number, nothing is missing from it. So any number that can be written as a whole number over another whole number is a rational number. So this rational number is still not just enough, because there are many rational numbers. So this rational number is still not enough. So mathematicians decided to break it down into 2 forms again. We have the integers, and we have, I don't know the name for it, there's no name for it, but I like calling it proper and improper fractions. Proper stroke improper fractions. So there's basically no name for it, but let me call it proper and improper fractions. Since proper and improper fractions are whole number over whole number, they are also rational. While the integers, now our integers are all whole numbers, both your negative and your positive numbers. So from your minus infinity down to -3, -2, -1, 0, 1, 2, 3, dot, dot, dot are your integers. All your positive and negative whole numbers are your integers. Now this 0 is there to complete the process. It does not mean that 0 is an integer. So there are actually several arguments on if 0 is an integer or not. If you go online, you will see that some people said it's an integer, some are saying it is not an integer. Several opinions on it. My own opinion is that instead of us arguing if it's an integer, let's just call 0 a real number. So that will settle everything. Let's call 0 a real number. That will settle everything. Now, integers. Now let me talk about our natural everyday life. Now you are a student of Delta State University or you are a student of the University of Benin or any other university, and you go to a market square and you want to buy something. If you get there, will you ever say you will have -30 naira or -100 naira? When you do that, those market people will never understand what you are saying, because in real life what we actually use is actually the positive whole numbers. We actually do not make use of the negative whole numbers. You cannot go and buy something and say I have -30 naira, or meaning that you are owing 30 naira. No, this is mathematics. In mathematics, that's where we consider these negative numbers. But in actual sense, in real life, what we actually use is just positive numbers. So these positive numbers is what we now call the natural numbers. So because we naturally use it every day, we tend to call it the natural numbers. So the natural numbers are all positive integers. So let's call it all positive integers. So from this 1, 2, 3, 4, 5, 6 upward are what we call the natural numbers. But once we include both the negative and the positive, they become integers. So when we talked about subsets and set, we said subsets are under the universal set. It means that the natural numbers are subsets of integers, while the integers are subsets of rational numbers, and the rational numbers are subsets of real numbers, and the real numbers are subsets of the complex number. We can also say that the natural numbers is a subset of complex number, or we can say the natural number is a subset of rational number, or we can also say the natural is a subset of this, whichever way you want to put it. Now let's talk about the irrational numbers. Now all irrational numbers cannot be written in this form. So examples of such irrational numbers are your surds, square root of your non-perfect squares. Square root of 3 can never be written as whole number over whole number. So your irrational numbers are those numbers that cannot be expressed as A over B, where A and B are whole numbers. So examples of that, we have your surds, we have exponential 1, this is your E, we have pi. Now this is where the problem comes, this is where the question in your mind is. You were told that pi is an irrational number, but in your secondary school you were told that pi is 22 over 7. 22 is a whole number and 7 is a whole number. So why am I not confusing you and telling you that pi is irrational and we are saying that pi is 22 over 7? So let me correct it now as you are watching this video. Pi is not 22 over 7. Pi was never 22 over 7. Pi will never be 22 over 7. That is why anytime you are solving your circle problems and you are asked to find the radius of a circle or find the circumference of a circle, they always use the word take pi as 22 over 7. They never said pi is 22 over 7. They say assume that pi is 22 over 7. So quickly, let me give you a brief history of pi. Pi started a very long time ago. Pi was initially not 3.142. It was a very funny value, I think 4 point something or less than 3.142. So how pi started was, if you have a circle and you measure the distance around this circle, that distance you measure around this circle, if you divide it by the diameter of the circle, you will get a value. That value, keep it. If you take a bigger circle, probably your drum set or your cover of any pot or anything, and you take the distance around it and you divide it by the diameter of that circle, you will get an answer. That answer you got here will be the same as you got here. That answer you got is what we call pi. But where mathematicians did not agree, they said you cannot actually measure this distance accurately. That is where they said no, you cannot actually measure it accurately. So the proof of pi started. If you have a square, comparing it with a circle, they don't look alike. But if I increase the number of sides to a 5-sided polygon, this look more like a circle than this. If I decide to increase it again, this look like a circle more than this. If I increase the size, so it becomes like a circle gradually. That is why sometimes we say a circle is an infinite-sided polygon. So what they do, they put this inside and put a bigger one outside. They will carry out the analysis. So at first, what they proved as pi, they did about 100 and something sided polygon, until someone did over 12,000 sided polygon to prove the value of pi. So after proving that, we ended up using 3.142. But after many years, they observed that 22/7 is almost the same value as pi, but it is not the same. So pi is irrational. Pi is not 22/7. Pi will never be 22/7. Pi was never 22/7. So that's for your real number system. Now let me tell you how we represent them. Now if you are given a problem and you are saying x is an element of arrow, probably they are telling you that A is a set of 4x such that x is an element of arrow. What this means is that x is an element of real numbers. That means x is a real number, meaning that real numbers are represented with the letter arrow. Our irrational numbers are represented with the letter I. Our integers are represented with the letter Z. And our rational numbers are represented with the letter Q. Our natural numbers are represented with the letters N. So sometimes when we talk about binary operation, our next topic, binary operation, you will see some questions that they will ask you, find blah 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 and so on, and they will ask you that x is an element of integers. You will solve and you get it wrongly because they restricted you to integers. So anytime you see this letter N in set problems, what they are telling you is that it is an integer, it is a natural number. Anytime you see this alphabet Z, they are saying it is an integer. Anytime you see Q, they are saying it is rational. Once you see I, they are saying it is irrational. Once you see arrow, they are saying it is a real number. So quickly, let's solve two questions based on our last video, and we'll wrap it up for this video. Two questions based on our last video. The first one, if the universal set is I'm giving an instance. Let's say the universal set is a set of all x such that x is an element of a natural number, meaning that our natural numbers include 1, 2, 3, 4, 5, 6, and so on. And A is 1, 2, 3, 4, 5. Our B is 2, 4, 6, 8. Let's stop here. The question says, find A union B. 2, find A intersect B. And 3, find A minus B. 4, find A symmetric B. Although there's nothing that will make us use this universal set, but I just put it there so that I can explain how you see some of these questions. Now we have the first question, A union B. What did we say union is? Adding up the elements in A and B. So the elements in A and B, joining them together, we're going to have 1, 2, 3, 4, 5, 6, 8. So our A union B is 1, 2, 3, 4, 5, 6, 8. And our A intersect B for question 2 would be those elements that A and B have in common. Those elements are actually 2, 4. So the elements they have in common is 2 and 4. Then lastly, okay, for the third one, we have A minus B. which are those elements that are in A but not in B. The elements in A that are not in B is 1, 3, 5 because they are not in B. So we have 1, 3, 5. Then for our A symmetric B, it includes those elements that are in A but not in B, and adding it up with those elements that are in B but not in A. So since we know those elements that are in A but not in B, let's first of all look for those elements that are in B but not in A. The elements in B that are not in A includes 6 and 8. So we have 6, 8. So therefore, our symmetric difference of A and B would be 1, 3, 5, 6, 8. So we have 1, 3, 5, 6, 8. The question could have been, what would be A minus B prime? Meaning that we will now be working with the universal set. A minus B prime, we have gotten our A minus B as this. What are those elements that are in the universal set that are not here? They include 2, 4, 6, 7, 8, 9, 10, and so on. So I can write A minus B prime. We said these are natural numbers. We include 2 is not here. We include 4. We include 6, 7, 8, 9, and so on to infinity. So these will be the elements that are in the universal set but are not in this A minus B. So that will be all for this video. Please do not forget to like and subscribe to SQC Tutorials. Share this video, comment. Your comment is very much appreciated. And if you are having any issues with your MTH 101 and 110 or any part of which you feel I did not explain for you properly, that you need more explanation, please state it in the comment section. I will do more videos for you to understand. Your success is our concern. Thanks for watching.